Welcome to Physics 30 Prep Fast Track, Lesson 2-5, where we'll talk about gravitational fields. And of course, when Isaac Newton was able to describe mathematically how gravitational forces controlled the motion of the planets, he was not able to explain the source of the forces. However, we don't need to know where gravity comes from. We can know how it works, as you further your studies in physics, you can possibly look for explanations of why. But he stated the gravitational law as two masses attract each other. All right. When two masses interact, they always attract each other. Now, what this symbol means, as we talked about earlier, this symbol means is that the force of gravity is proportional to the product of the two masses. So if the two masses are very big, the gravitational force between them is going to be much larger. If two masses are very small, then the gravitational force will be much smaller. And that's what he's basically saying. The attraction is larger if the masses are larger. The force varies directly with the product of the masses. Now, Newton also said that the gravitational force of attraction gets smaller exponentially as the masses move apart. What he's saying here is that the gravitational force is proportional to the inverse. All right, this is an inverse, and so what he's saying is, as the distance between two masses gets larger, the force gets smaller. And if you double the distance, you would quadruple, or you would actually decrease the gravitational force by 1/4. If you tripled the distance, you would decrease the gravitational force by 1/3 squared, which is, of course, 1/9. Henry Cavendish was able to prove Newton's ideas by using something called a torsion balance. And he also was able to provide something called the gravitational constant, or the universal gravitational constant. Since the force of gravity is proportional to the two masses combined, or that is multiplied, and it's also proportional to the inverse of the distance squared, Cavendish was able to measure the force at different points between two masses. And as he moved the masses closer and further apart, he was able to plot those points. And what he did was he plotted 1/r², and he got that from Newton, and he plotted the force of gravity. And when he plotted those together, he got a straight line. And of course, a straight line means a direct relationship. And so when he took the slope of this, he actually found that the slope was equal to G m1 m2. And then, of course, since he knew the two masses m1 m2, he was able to calculate the value for G. Now, this value for G is the same anywhere in the universe. It doesn't matter where you go in the universe, you will find the same value for big G. Remember, little g, 9.81, changes as you go from planet to planet. But big G stays the same, and its value is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And so taking Newton's relationships, that is the proportionalities here, once you have a constant G, then you can make it into an equation. And Newton's equation is the force of gravity is equal to the gravitational constant, so that's always going to be 6.67 exponent 11 negative, times the product of the two masses, whatever those two masses are. Could be the Earth and you. And of course, the distance r is going to be the distance between the two masses. Now, one thing we should remember, it's the distance between the centers of the two masses. So when we calculate the gravitational force of attraction the Earth has on you, you go from the center of the Earth to the center of you. And so it's not, even though you're touching the Earth, you're still quite a distance from the center of the Earth. So we would use that value r. So once the formula has been derived and explained, a student can then use your simple algebraic tools to solve for any one of these variables. All right, so you start with Fg is equal to Gm1 m2 over r squared. Of course, G is a constant, so it doesn't change. All the others are variables, and I'll just show you that the formula can be easily manipulated for each of these different unknowns. So here's the original. We're solving for g. What if we wanted to solve for m1? Well, we would multiply both sides by r squared and divide both sides by g m2. And that would leave m1 by itself, and fgr squared over gm2 would be on the right. So that's the manipulation for m1. For m2, same thing, except we would move m1 instead of m2. So here's the solution for m2. And if we want to solve for r squared, we basically just change these two. We put the r up on the top left and the fg on the bottom right. So r squared is equal to gm1 m2 over f, and of course to get r we would have to then take the square root. But since g cannot be changed, but as you change or manipulate any of the other values, the force of attraction will respond. All right. So if you make the masses bigger, the force of gravity will get bigger. If you increase the distance, the force of gravity will get smaller. All right. So looking at an example of the attraction between the Earth and the Moon, it says the Moon's center is 3.9 times 10 to the 8 meters from the center of the Earth. The Earth has a mass of 5.98 times 10 to the 24, and the Moon has a mass of 7.36 times 10 to the 22. What's the force between them? Well, this is a fairly straightforward one. We use the formula that Newton came up with a little help from Cavendish. We say g times m1, which would be the mass of the Earth, m2, mass of the planet, and r is the distance between them. So as we substitute, here's g, mass of the Earth, mass of the Moon, and of course here's r, the distance between them, and don't forget to square that. When you do this, you get a force of gravity of 1.93 times 10 to the 20 newtons. And of course, this is the force that the Earth exerts on the Moon. It's also the force that the Moon exerts on the Earth. Remember, Newton's third law says that every time there's a force, there's an equal and opposite force. And of course, the acceleration will be much greater for the Moon because it has a smaller mass. So that's why the Moon goes around the Sun rather than, or sorry, the Moon goes around the Earth rather than the Earth going around the Moon. And of course, a bigger mass, since the forces are the same, a bigger mass gets a smaller acceleration. A smaller mass gets a bigger acceleration. Another example, an object is 1.9 times 10 to the 7 meters from the center of the Earth. The Earth has a mass of 5.98 times 10 to the 24, and the object experiences a weight or gravitational force of 655 newtons. What's the mass of the object? In this case, what we're giving you is we're giving you the force of gravity, and we're giving you m1, the mass of the Earth, and we're telling you how far r is, or that is the mass is from the center of the Earth. What we're not giving you is we're not giving you m2. So we manipulate the formula and solve for m2 by multiplying both sides by r squared, dividing both sides by gm1. When we substitute, this is the weight of the object, this is the distance of the object from the center of the Earth squared. Here's big G, and here's the mass of the Earth. When we punch that into our calculator, you should get 593 kilograms. So that object that is probably in orbit around the Earth is has a mass of 593 kilograms. So good example, just your straight formula, and then you manipulate for an unknown. All right, here's another example. It says a mass of 1.9 times 10 to the 5 kilograms is in orbit about the Earth. It experiences a gravitational force of 2.91 times 10 to the 4 newtons. The Earth has a mass of 5.98 times 10 to the 24. How far is the mass from the center of the Earth? Once again, we start with Newton's basic formula for universal gravitation. This time, we're giving you, g of course is a constant. We're giving you the mass of the Earth. We're giving you the mass of the object. We're giving you the force of gravity acting on that object. What we're not giving you is r. So what we do is manipulate the formula for r squared, and of course that just means dividing both sides by fg, and multiplying both sides by r squared. When we substitute, big G, here's m1, here's m2, here's f, and we get r squared is equal to 2.604 times 10 to the 15. But remember, this is meters squared. R squared gives you meters squared. So to find r, what do? We take the square root of r squared, and that gives us 5.10 times 10 to the 7 meters. These are excellent little examples of the kinds of problems that you need to be able to do. So from the first example, you see that the force is the same, the acceleration would be different. And of course, that's because surrounding any object, you have a gravitational field, all right? And of course, this gravitational field is what causes the gravitational force, all right? So the gravitational field strength is dependent on the mass of the object producing it. And so in order to find out the gravitational field around an object, you can take your basic formula for force of gravity, which of course is given in Newton's universal law. Of course, since the force of gravity is equal to mg, then g is equal to the force of gravity divided by one of the masses. We use m2. All right, we divide by m2. Usually the bigger mass we call m1. And so when we divide m2 by m2, those m's cancel, and we're left with the gravitational field strength, or g, or the acceleration of gravity, same thing, right? Acceleration of gravity and gravitational field strength are the same thing. Then we get the force of gravity divided by m2 gives us gm1 over r squared. And so our formula is g is equal to gm1 over r squared. And an object on the Earth will experience a gravitational force of g is equal to gm1 over r squared. Here's g. Here's the mass of the Earth. Here's the distance, the average distance an object is. This is the average radius of the Earth. So this is, if you're standing on the surface of the Earth, this is approximately your distance from the center. And what we get is 9.83 newtons per kilogram, or 9.83 meters per second squared. Now this is an average for the entire Earth, all right? Because we're using basically the average radius for the Earth. But in different parts of the Earth, such as in North America or Canada, we're a little closer to the center of the Earth, and therefore our gravitational field strength is a little bit different. So we use 9.81 meters per second squared, or 9.81 newtons per meter in Alberta. The distance from the equator changes r, and therefore no matter where you are in the Earth, r or g could be a little bit different depending on your location. And so one last example is dealing with gravitational fields. If you had two identical masses, m1 and m2, and they were situated on an east-west line, and they were 10 meters apart, what's the gravitational field strength at a point 7.5 west, or meters west of m2? So what they're saying is, at this point where the star is, what's the gravitational field strength? Well, it's going to be the sum of the two gravitational fields. One is produced by m. M is going to attract it in this direction, and m2 is going to attract it in this direction. Now, some of the things you have to understand here is, because this object here is closer to m1, the gravitational field strength there is going to be stronger. Because it's so far from m2, it's going to be weaker. What you need to do is find out the gravitational field due to the first mass, m1, and then find the gravitational field strength due to m2, add them together as vectors. And so here's g1. g1 is equal to gm1 gm1 over r squared. Here's g times the 40 kilograms, that's m1, and the distance from m1 is 2.5 meters. Don't forget to square that. You get 4.27 times 10 to the minus 10, a very small gravitational field strength to the left. Notice the units. It can be newtons per kilogram or meters per second squared. They are the same unit. They are identical. Okay? And then, of course, G2 is going to be the same, only we use the same value for G. M2 is 40 kilograms, but R is much bigger. So because we're further away, we get a smaller gravitational field, and it's only 4.74 times 10 to the minus 11. Here it's 10 to the minus 10, which is quite a bit bigger. So one is about 10 times larger than the other. So then we add them together. And of course you add them together as vectors. Let's make west positive and east negative. So the west being positive, we add it to the east force or field being negative, and of course what we end up with is, overall, we end up with a net gravitational field that is positive, because the M1 is, since it's closer to M1, we experience a stronger gravitational field, and so the net gravitational field is to the left. And we say it's 3.79 times 10 to the minus 10 newtons per kilogram or meters per second squared. And of course the direction, because we said west is positive, it's going to be west. And of course we add these as vectors, and a third mass placed between the two masses. So if you did place a mass right at the star, it would experience an acceleration towards the west due to the gravitational fields of both of those. Okay? And that is a little bit about gravitational fields that you should know.